Hi, let's get started. Okay, hey guys, welcome to the last reading group session of the term. For anyone who's new here, Ashley and I are going to be presenting two papers in the field of LLMs and transformers. And yeah, I would normally say like if you have any ideas for the next reading group session, but there won't be. This is the last one. Applications, I believe, are still open for like execs for the later term. So if you'd like to host a session like this later term, or if you want to host like workshops or anything like that with the education group, applications are open. I would encourage people to join and sign up. So for today, the two papers that we're going to be going over, first paper, RetNet, is a bit ironic since our like session is on transformers, but this paper suggests an alternative to transformers, which has like shown like considerable improvements in performance. And the second paper is gonna not be actually a paper, it's more of a topic, and I'm gonna be going over multiple papers within that field, and it will be on LLM powered autonomous agents. So to get things started, Ashley, the floor is yours.
Great, thank you so much for that intro. I'll hop right into it. The paper I'm doing is a little screenshot of the first page here. It's called Retentive Network, a Successor to Transformer for Large Language Models. The disclaimer I want to put here is just that it's definitely not the first time someone's proposed a successor to the transformer, and we're still actively using them as the kind of state-of-the-art model. But if you are interested in looking into this further, two other examples of this are the attention-free transformer proposed by Apple and RWKV proposed by BlinkDL that are trying to achieve similar things. And also, I find these ideas pretty complex. And so I've been wrapping my head around this paper for like the last couple of weeks and still find understanding the details a little bit tricky. So I apologize if I don't explain it in sufficient detail or well enough, but feel free to ask questions and I'd love to discuss it some more. So the context you need to understand where this paper is coming from is first that transformers are something that exists. They're the fundamental building block of most large language models we hear about. If you want to learn more about transformers or the paper that first proposed them, we actually had a workshop on transformers and an event on the paper. Attention's all you need. And there's some screenshots of that here. Feel free to poke around at it further. But what you need to really understand is much simpler than that, and it's that the transformer architecture is great because it lets you efficiently parallel process sequences, and it has really good performance. It can understand really complex stuff. The con, though, is that when it's making predictions, so when it's doing inference, it's extremely expensive. It's of order n squared, where n is the sequence length. So that'll be, I think my understanding is that means like the collection of like the amount of tokens or words you have in your input. So the takeaway is it trains really fast, but it's slow when it comes to doing inference. The other thing that exists out there that's often used for these natural language processing tasks is a recurrent neural network. And the pros of the recurrent neural network is it's very efficient at inference. It'll do it in only ON. And then the cons are that it has an inability to process parallel sequences. So it has to do it one token at a time. And therefore, it can't train in parallel. It can't train really quick. And in general, we don't see as good of performance coming out of the recurrent neural network. So the takeaways from that is it's slow at training, but fast when it comes to inference. The third thing that exists there out in the world is called the linear transformer. The idea of it is that it's similar to a transformer, but it's made more efficient, where it also has the same ON inference time as the recurrent neural network. And one of the key result little snippets I have here from the paper it was proposed in is that our linear transformers achieve similar performance to vanilla transformers, and they are up to 4,000 times faster on autoregressive predictions of very long sequences. That's really promising, but everyone else who kind of reviews this paper seems to come to the consensus that the performance isn't necessarily as similar as they say here. So that leads us to this diagram I have on the right, where we have the linear transformer that can train in parallel because it's like a transformer, and it also has low cost inference, like I was showing you that ON time for inference. And then the recurrent neural network that also has that same low cost inference and pretty strong performance, but the transformer has even stronger performance and can train in parallel, but has pretty expensive inference. Then RetNet is what this paper is proposing, and it's hoping that it will be the new foundational model for things like these large language models. It's based on the retention mechanism, which we'll be touching on, and it's said to achieve this impossible triangle here. So diving into the methods, the layout of it is really similar to the transformer. So it's keeping a lot of the good stuff, but replacing one of the core parts of the transformer called attention with this retention module. And each one of the RetNet blocks has two modules. The multi-scale retention module, which is this innovative part we've been talking about, and then a feed-forward network module, which has definitely been done before. So in terms of the retention module, I just want to make sure everyone can still see my slides, right?
Yes, yeah.
Okay.
Retention mechanism slide.
Perfect, thank you. I have it up on another screen and it's showing slightly different, so thank you very much. So there's two sort of representations of this very mathematical set of formulas they present in the paper. And the first one is shown on the left with an A next to it. And it's the parallel representation, which shows how something like this can be trained in parallel, which is the best part of the transformer. And then B, which is on the right, shows how it can be use recursion, and that allows for really efficient inference, which is the best part of the recurrent neural network. I think it ends up being more detailed and than this, where it actually uses something called chunk-wise retention, where on each chunk, it's able to parallel process the chunks, and then there's some sort of recurrent connection between the chunks. But it definitely gets a little theoretical at this point, and I wasn't able to completely keep touch with everything. But their experiments and results, this is the really interesting part. So in terms of training data, they used a bunch of these big corpuses of both text and code. So you can see that I've kind of outlined three here that they've selected their data from. And they're using a batch size of about 4 million tokens that have a maximum length of 2,048 tokens per sequence. So then the first thing they look at is perplexity. So this is a statistical measure of how uncertain a language model is in its predictions. So you want lower is better, because you want it to be more certain and not more uncertain. And so here they only have 3 data points, but they compare a transformer to a RetNet of model sizes 1.3 billion parameters, 2.7 billion parameters, and 6.7 billion parameters. And it shows that perplexity decreases with model size for both, but that the RetNet has better scaling, where it goes down linearly, whereas the transformer doesn't go down quite so linearly. The other thing they look at is 0/few shot learning. So here, what they're doing is they're using these benchmark evaluations that'll, some of these are like yes/no questions, for example, that the transformer has to, or the RetNet has to guess what the answer is. And if it gets it right, that counts in favor of it. And if it gets it wrong, it counts not in favor of it, which is a pretty simple way to analyze these things. And it's using the larger model size, which we saw on the previous set of slides, performed better in terms of perplexity than the transformer. And when you look at the results of these benchmark evaluations, you see that the accuracy that the RetNet gets is either equal to or better than the transformer, which is pretty interesting to see. And that zero shot is, in case we haven't gone over this recently, when you just ask it one of the questions out the gate. And four shot is often when you give it some examples to go along with that question to kind of help it lead better along. And then for inference, they're looking at the amount of memory, time, and throughput that the model takes when doing predictions. And we see that it does better than the transformer on all of these because the RetNet model performs with, made a slight mistake here, constant GPU memory usage, constant throughput, and constant latency, whereas the transformer often scales at about order n with respect to either the sequence length or the batch size here. So the key result coming out of this is that RetNet improves decoding throughput, latency, and GPU memory without sacrificing performance. Here are some kind of summary plots where they compare the GPU memory as being lower, the throughput as being higher, and the latency as being much lower than the transformer, and then the same perplexity curve as we saw before, showing that it scales better. So when we compare these results to some of the other models we've talked about, we can see that it gets 2 check marks for performance, showing that the RetNet and transformer have some of the best performances of these models outlined, that they're able to train in parallel, and that the inference cost of the RetNet is similarly low to like the recurrent neural network, and that the memory complexity is also similarly low, like the recurrent neural network. So based on the results we see so far, it does seem like it achieves this impossible triangle of good performance, fast inference, and ability to train in parallel. Now, looking forward, what the paper says is that they hope to use RetNet as a backbone architecture for multimodal large language models. Multimodal is when it's using more than just text, so it'll use at least like one other kind of communication medium. So here's one of the examples I think we talked about last term with the GPT-4 paper, where you can input an image and a question, what would happen if the strings were cut? And then you want the large language model to return something like GPT-4 did here that says the balloons would fly away, showing it has an understanding of both the text and the image. And then also the hope is to deploy RetNet on edge devices like mobile phones. This is an extremely exciting thing to talk about because mobile phones are nowhere near the level of compute power that they could run something like GPT-4 themselves. But if things actually scale as well as is shown in this paper, and the compute demands are actually a lot lower than the transformer, it means that some of these models could run like locally on something like a phone. In terms of limitations, the weaknesses the paper says is that the behavior is not well explored for larger model sizes. Often we're seeing like the state-of-the-art large language models be quite huge. And so exploring those larger model sizes is really important. And then a more significant number of training steps also wasn't well explored. From my perspective, when I read this paper, the 2 weaknesses that stood out to me are that one of their main results is that perplexity plot that has the 3 data points. But I just very rarely see 3 data points as being enough. There's nothing to say that like one of them might not be some outlier, and that they just seem to train only 2 models with specific hyperparameters and didn't, I think, really well explore it as much as they could have. So I think it would have been nice to see that more extensively explored, even something more like 10 data points to make sure that the actual relationship you're seeing is true. And then the benchmark evaluations they used, I looked at the papers, they seem legit, they seem to be used by a lot of other people, but it was really cool in the ORCA paper we did at the start of the term to see that they used benchmark evaluations people like me had heard about before, like Big Bench Hard, and then academic exams like the SAT, LSAT, GRE, and so on. I'd actually be interested if people have any opinions on why these weren't used here. One of my thoughts was maybe that it's very dependent on like the training data you have, and that wasn't their focus to give it a wide variety of training data in this paper. But I thought it was interesting that they didn't use the same sorts of comparisons as we've been seeing in some other papers lately. Then there's some additional criticisms that people have put on this paper. The first being that it overstates the novelty of these ideas and how much better it is than some of the other alternatives that have been proposed. They also say that perplexity is not a great holistic measure of performance, and that more of these benchmark model evaluations should be used for the model. And then we're seeing more and more how important it is to be able to process long sequences, something that's much longer than 2048 tokens, for example, and that's not really well explored in this paper. And if it doesn't work well on longer sequences, that's a really big downside to this model. I'm sure there's a lot more things out there in terms of criticism. There seems to be a lot of discussion about this at the moment, but in general, people also did seem impressed, especially with the speed at which it can make its predictions with. So hopefully we can just have a little moment to discuss either this paper as a whole, or if nothing's come to mind in terms of questions, I have one for you guys. So one of those things this got me thinking about was what sorts of results would you need to see to believe that a model proposed like RetNet would actually be the successor to the transformer? Are these results enough? Are there anything else specific that you'd want to see? So that's it for me today, but I'd love if we could chat about this.
I think the metrics that you posed, like the SAT tests or the ones that were like previously, the ones that you previously covered from the like ORCA paper would be like a good metric, because those are the sort of tasks that like users of models like this actually end up, using or like doing. And like having that in parallel with like the performance gains that you get from using a RetNet as opposed to like a transformer-based language model would be, like convincing enough.
Yeah, that's super interesting. And I was also thinking, even just for, obviously it's way too much to ask for this first paper, but like I think I don't know the ins and outs of how to train a transformer, but I know with like another like a neural network, I can easily make a neural network perform pretty terribly based on the hyperparameters I set for it. And so I feel like a really good test would be like, can they make something of similar performance to like a GPT-4 that runs on this architecture and then just does all of this stuff faster, other than just some random transformer that they made themselves?
Yeah, that would be pretty cool. Awesome. I guess if no one has any thoughts, great work, great work. Thank you for presenting this. And yeah, on to the next paper. Okay. Like I mentioned, today I'm not going to be going over a specific paper, more so a general idea. I'm like just going to be going over a number of papers that were presented related to this topic. And the topic that we're going to be going over is using large language models as autonomous agents. So I just need to mention that I got inspiration to cover this topic based on this blog by Lillian Wang. I've left a link for the blog in the slides, and be sure to check it out. It goes a bit more in detail and covers like a more holistic view of the topic. I'm just covering certain aspects of it. But yeah, her blogs are like a great resource if you need to touch up on anything really like machine learning related. She tends to go over a lot of topics that are pretty new in the field, a lot of topics that are, yeah, like interesting coming up new, and she has like a really good way of explaining them. So I highly recommend. Okay, so context on language models. This paper came out in 2020. Language models are few-shot learners. This was at the time that GPT-3 was released. This paper was published by researchers at OpenAI. They just tested or like formally tested the performance of language models like GPT-3 on few-shot tasks. What are few-shot tasks? Few-shot tasks are you just give the model a certain task that you want it to do, and then you give it a few examples of like similar cases and what the expected output should be, and then you ask it the specific question that you want to ask, and you get its response. And yeah, just an example of this, like let's say you give the model a prompt, translate a sentence from English to Arabic. You give it a few sentences, like example sentences, like machine learning, red cat, and then you ask it to translate angry goose. This is an example of few-shot learning. We've gave it 2 previous examples. And this paper showed that language models such as GPT-3, given like enough data and given enough like a big size, perform really well at few-shot tasks. And yeah, like the key behind this, or not the key, sorry, the key result from this is that you can use language models on a wide variety of tasks, and it has the ability to adapt to each of those tasks that you ask it and perform really well. So in a sense, language models from that point onward, you can kind of consider them as like this like little child that you have. Oh no, let me use my words wisely here. Language models are like this worker that you have, this employee that you have, and in a sense, you can give it like any task, and you can have it communicate with other employees or like communicate with other people and perform that task effectively. And so people using these large language models have been trying to build full-fledged systems in order to perform certain tasks that you want it to do. Now, these systems that are being built based on large language models consist of 3 main components that people have been trying to make more effective and more efficient. Number 1 is giving this large language model agent the ability to plan. So you give it a certain task, you want it to be able to break down that task into a set of steps or a set of achievable sub-goals, and then work on each one. Number 2 is you want to give this agent memory. So it would learn from previous results that it had, or previous results that it did, or previous results of not just itself, but other people that have experience doing a task like this. And number 3 is you want the agent to have the ability to use tools. So for example, your agent might not be good at, like your language model might not be good at math. You want to help break any math tasks that it might encounter into sub-goals that could be, for example, solved using a calculator, like if it had help from a calculator, or let's say it you wanted to do some coding related tasks. So in order to help it with that, you might want to use like a code interpreter, for example. And one thing that I want to point out with these systems is that it's similar to like us as humans. Given a certain task, how would we solve this? Like we would rely on our memory, we would break down this task, we would use certain tools to assist us. And in a similar way, we want a language model to have those similar abilities. So let's take a look at each one and break them down a little bit. In terms of planning, can everyone see my screen? I just want to make sure that we don't have any issues. Everything's going a-okay.
It's still on LLM agent systems.
Yeah, okay.
But it looks good.
Sweet. Okay. So number 1, in terms of the planning stage, in terms of having your model think step by step, one thing that people notice is that if you have your language model, when you ask it to do a certain task, if you have it explicitly before coming up with like a solution, have it explicitly like explain its step-by-step process, that usually yields better results. So this paper in 2022 came out where, let's say you want to ask your language model a specific question. And this is, let's say, a few shot example where you give it like previous examples of similar questions and how you'd want the answer to be laid out. In those previous examples that you mentioned to your model, if you have the answer explained step by step, forcing the model when it goes to produce its answer for its question to lay its answer step by step, that usually produces better results. Actually, let me pull up the paper real quick because chain of thought prompting, the example that they show is like a better visualization of it. So let's say you have a certain math problem that you want your model to solve. Like the cafeteria had 23 apples. If they use 20 to make lunch and bought 6 more, how many apples do they have? You give it a previous example in your prompt. You just specify like a previous example of a similar math problem. Like Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have? And the like answer to that previous question, if you just give it direct, the model itself, when it goes to produce its answer, would give a direct answer. And that usually produces incorrect answers, specifically in like problems that like math, for example. But instead, if you have your exemplary answer be laid out step by step, Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 cents, whatever, and then produce the answer. The model itself would learn to produce answers step by step, and usually that yields better results. Okay. So that is chain of thought. Another one where you have the model like explicitly lay out its thinking. Let's say you put your model in like an environment, you ask it to do a specific action. If you explicitly tell it, okay, think before you produce that action and have it lay out exactly its thoughts, once again, produces better results. This paper is called React, published 2023. Now, so that was previous examples, actually like common tricks that you guys can use whenever you're using like GPT, just like if you want it to answer like a specific math question, just in your prompt include previous examples with like lay down step by step, ask it to lay down its answer step by step, and it will yield better results. Now, moving on with this like planning phase. In your large language models, if you want your large language model to also like be able to plan, people have like devised ways of creating like explicit planning systems. I'll go over this first example, tree of thought. I think it's such a cool example. Like, let's say you ask your model to like solve a certain math problem, similar to the one that we saw. Similar to the one that we saw here, like this Apple math problem. What you can do is you can have the model first, when you ask it the question, tell it, okay, suggest 3 possible next steps that you can go from here in order to solve this question. It would suggest 3 possible next steps. Then you ask your model again, okay, from these 3 possible next steps, which one do you think is the best next step? It would pick, for example, the second one, and then you'd go to that next, like second next step. You use that as your action, I guess. Ask the model again, okay, from this point onward, what do you think are like 3 possible next best steps that you can take? It will suggest 3. Ask it again, what do you think is the best one out of these 3 that you suggested? You keep on doing that until you converge onto your solution. And that whole trajectory of the like the steps that the model picked is, I guess, the thought process of the ideal way to go about solving this problem. And yeah, this is like a visualization. You ask it to like propose 3 steps, then ask it select the best one, select the second. From that point onward, ask it to like suggest another next step until you get to your output. That's called tree of thought. I think also proposed by researchers at Google. Another way of like having your language model be, I guess, a planning system, like this is an explicit way of planning system. You actually, yeah, it was proposed in this paper, Reflection, published by researchers at Northwestern University. The person that published this was actually an undergrad. Crazy stuff, whatever. It's essentially reinforcement learning, but instead of having explicit vectors, you have everything with like a natural language interface, and you have like language models sprinkled in. Let me explain that a bit more. In reinforcement learning, you have your model presented in a specific state, and you ask it which next action it should do. In this case, we have an actor LLM. You present it a certain state, like, okay, this is like the chessboard, for example. You're in this state, the pieces are in this position. What move do you think we should do next? You have your actor LLM suggest a new move. You perform that new move. Your environment like might return some reward, like, oh, that move was good, that move was bad, and then it just returns what happens in the environment after you do that move. You then get another large language model. You give it the action that was done, and you give it the results that you got as a result of doing that action. And it, I guess, reflects on, was that a good move or was that a bad move, and like why it was a good move or why it was a bad move. Presents those self-reflections back to the actor, and that helps the actor when it goes to decide the next move that it wants to do. So yeah, that's reflection model. Now, on to the next piece of the puzzle, and that is tool use. Tool use, I think, is probably the most important piece of the puzzle here. And that goes back, and the reason I think so is because of the nature of large language models. They're autoregressive models. They're essentially like probabilistic models. You can't really control the outputs that your models are going to get. But with the use of certain tools, like Wikipedia or like calculators or previous data from like Excel sheets, you can essentially ground the outputs that you get from your model. You can like essentially verify, oh, was this output actually correct, or is it just hallucinating and producing incorrect results? So yeah, I think tool use is probably the most important piece of the puzzle here. And yeah, like over the last 2 years, researchers have been devising ways to get your large language model to like call on certain APIs or use certain tools when it needs. One of those methods was suggested in this paper called toolformers. When you're training your large language model, you just essentially ask it, okay, in this given sentence, where do you think a good place to perform like an API call or to use certain tools would be? After that, you perform those certain API calls and you test which ones actually help the model produce correct results or predict like the next words after that. And after you filter out those API calls by the ones that actually were effective and actually were helpful, you retrain the model based on the text with the new API calls like embedded in between. And as a result, you have a model that knows perfectly when and where to like, or not perfectly, but like it knows when and where to call certain APIs that would help it produce correct results. So yeah, that's onto tool use. Onto the third piece of the puzzle, and that's memory. In the prompt that you have, like the prompt that you give the model, that people consider to be like a short-term memory. You can kind of suggest or you can include in the prompt that you include to the model, or that you give to the model, things that happened in like previous steps or stuff that happened in previous events, and the model would be able to like reference that when it's calculating what it thinks should be the next step. But an issue with the like prompt that you give it is that they're of a certain like length. People have been working on extending that, but reality is we can only stick to a certain length. So people have been devising what are known as like long-term memory systems and have been relying on something called vector databases. Now, what are the vector databases? Vector databases basically store data inside this table, but this table, like the values that are stored in this database, are indexed by like coordinates on a vector space. So what you could, for example, include in your vector database is previous encounters that the model had, like previous states that it was in, what action it did previously, and what rewards it got, or like what punishment it got, I guess. And yeah, in this like vector space that you store them in, memories that are like closer to each other, or like memories that are similar to each other, are stored closer together. When a model goes to like encounter a new scenario, a new state, it just checks in this vector database which memories it had or which previous encounters it had that were like of a similar nature to the current example that it has. And it references what it did back then, what rewards it got back then, what results it got back then, in order to suggest a new action. So for example, yeah, here, this new encounter that it had on the vector space when you embed it in the vector space was around here. It's very much close to this first memory that it had. So when it goes to suggest a new action for this new encounter, it would rely on information that it had from this previous memory. There's like an algorithm that they follow in order to calculate like the closest memories that you have in a vector database. It's called approximate nearest neighbors. There's a couple of algorithms to do that. But yeah, that's just a way to make it faster. And yeah, with that, we've covered the three main like pieces of the puzzle that you have when you're creating a large language model agent. So for now, how well like do the current systems that we have actually perform, and like where have we seen them being applied? I've included three main examples, which I think are pretty cool. First one is this demo by students at Stanford. Actually, let me click on the demo link because it's pretty cool. It's essentially like a Sims-like environment where each character in this environment is its own large language model. And you just ask it, okay, you're in this state, what action do you think you should do next? And that determines how the character corresponding to that large language model like actually navigates through this environment and like what interactions they have. And yeah, I guess this is like a demo of it. You can see them, some of them take a shower, some of them sleep in, etc. Like as it goes on, you just see how they interact. And from this demo, like one cool thing was that they have shown signs of like intelligence. At some point within this demo, one of them like hosts a Valentine's Day party, and he invites a couple of friends that he has, and then they like spread the invitation over to like other friends, and they spread the invitation over to other friends, and they all then like at a certain time, at a certain place, they all like gather together, just similar to like what we have in our natural environment. So I think that was pretty cool. That's like, yeah, one example of this. You can imagine like building full-fledged video games with agents based on large language models, or you can imagine like writing a specific show, like an animation show, something like Rick and Morty, and having all the characters essentially be large language models. Like you don't have to explicit script, or you don't have to write like an explicit dialogue. You can just have your large language models like interact with each other. And I think they are doing that with South Park. I hope I'm not mistaken on that. So yeah, that's like one venue of it. Another venue is having like LLM-based assistants. You can tell your large language model assistant you want it to do like a specific task, and then it goes through the entire like planning phase. It references things that it has from memory and like from previous tools that it has in order to achieve those tasks step by step. Those are two examples of this. ChemCrow is an example for an LLM-based agent that was used for like drug synthesis and just in general like chemical experiments. And yeah, the model has the ability to like reference previous research papers, previous results, previous data, and just in general like any chemical knowledge that would be required to do certain tasks. And it has the ability to like break it down, assess each like step that it takes in order to achieve a specific task. Another one is like an LLM-based programmer. This is actually a tool built by a student at Waterloo. He actually dropped out of Waterloo to build this tool called Sweep, and he was funded by Y Combinator. And yeah, this tool is like a junior programmer. Basically, you ask it to like fix a specific bug that you have in your code base, and it goes through like a step-by-step process of analyzing your code, suggesting possible changes, filing a PR, etc. Unfortunately, I would say that the like idea is way too ahead of its time. I went on this like products page and it was like 1-star reviewed a couple times, which, like I said, I don't think it's a bad idea. I think it's just ahead of its time. Like it just needs a bit more time to like develop. But yeah, possible examples of using LLM-based autonomous agents. And yeah, with that, I guess comes the end of this session. My presentation. I actually have a question, like just a point of discussion. Do you guys think that we could ever reach a stage where we have like full-fledged assistants or full-fledged like programmers that are just built on top of like language models or on top of machine learning models with like almost little to no like human supervision or human involvement? Is that something that we could ever reach, or are we always going to require like human supervision at hand, or always going to require someone to go over it step by step because we don't really trust these models? Yeah, I guess I'll field in any possible answers.
I think Darcy had his hand up, so